It's one coil inside of another coil. And let's just turn the lights down for now. So just like I'm showing you, there's an inner coil and an outer coil. And the primary coil is where we're putting a voltage and a current in. And the secondary coil is where we're getting the output. So if what you put in here, if you just hook this up to a battery, then when you turn it on, you'll see a response because you're going from no flux to a big flux. But if it's just not changing, there'll be no output. So the way that you get a constant output is to have your input constantly varying. So let's read an 800 turn or winding coil has a diameter of this much and a length of that much and a resistance of so many ohms. The secondary coil is placed inside, this secondary coil is placed inside a larger 1000 turn primary coil. The axis of the coils are collinear. The diameter of the larger coil those are the dimensions, and its resistance is such. An alternating voltage is applied to the outer larger coil. The voltage is applied according to this equation. So let me write that down and let's So the equation for the voltage is V equals 12.8 volts cosine 2 pi t over 16 milliseconds. So let's understand what this means. So when t equals 0, this will equal 0, and the cosine of 0 is 1. So if I graph this, it's going to start at 12.8 volts. And this is radian measure. So when t equals 4 milliseconds, you'll have 4 over 16, which is 1/4. So 16 is the cycle length, called the period. Because at t, as the clock goes, when t gets to 16 milliseconds, this will be 1. And this will be 2 pi. And 2 pi is 360 degrees, right, in radians. 2 pi radians is a full cycle. So what this number is this is the period, and we use a capital T, the period of the oscillation. That's how long it takes to repeat. It repeats every 16 milliseconds. But we're going to this repeating thing has a frequency. And so it's important, and these equations are on your equation sheet. It's important to know, I think we've talked about this before, but not for a while. The frequency of any oscillation is just simply 1 over the period. So if you take 1 over 16 milliseconds, it means you get 1 cycle every 16 milliseconds. So period is given in seconds, like 16 milliseconds or 16 times 10 to the minus 3 seconds, however you want to do it. And frequency is given in cycles per second. So this is the seconds per cycle. And when you invert it, you get the cycles per second, which is what we know as frequency. And so if I change this to 1 cycle, 0.016 seconds, that's 16 milliseconds. And so if I take 1 over that, (62.5) cycles per second. So if something is taking 16 milliseconds to cycle, it will give you 62.5 cycles per second, and we have a unit for that. That's what's called a hertz. So when you talk about megahertz or gigahertz, you're talking about 1,000,000 to 1,000,000,000 cycles per second, because computers are very fast in doing operations. In the case of computers, it's the number of bits that it reads every second. Okay, so we do need to know the relationship between frequency and period. And there's another quantity that will come up in this assignment and later in the next 2 weeks. And that's that there's a quantity known as omega, which is the angular frequency. And we knew this from last semester's angular speed, so it was radians per second. So 1 cycle is 2 pi radians, right? 1 cycle equals 2 pi radians. So if we have if we take 2 pi, so 1 radian per second. If something's cycling 2 pi radians per second, anyway, I'm getting myself confused. 2 pi times omega equals the frequency. The angular frequency is much higher because you're measuring how long it takes every radian to appear rather than every cycle. So the relationship between angular frequency and cycle frequency is this relationship. And so this anyway, if we take this relationship and solve it for period, we get that the
frequency is
You
omega
get that
over 2
the
pi.
frequency is equal to the period divided by 2 pi, taking this equal to that.
I think it's,
It's
2
upside
pi
down.
over t.
Yeah.
Isn't it omega equals?
I don't know, but I'm just getting stuff here, so. What do you say?
It says on the equation sheet, omega is equal to 2 pi over t, or 2 pi f.
Omega equals 2 pi over t. So if you have, that's the number of cycles, and that's the number of radians. So if you had a frequency of 1, that would be 1 cycle per second. That would be 2 pi radians per second. So,
Yeah, you're correct.
anyway, something's confusing me here, but anyway, so that's the other relationship that we will use. And so what we have here is we have 2 pi over t, so this could be written. Another way of writing this that you'll see later is, in general, this relationship will be 2 pi, since it's in radians, over t times the time. And so this could be written as the cosine. It's actually simpler written as the cosine of omega t. But anyway, I'm writing it this way because it's more transparent what's happening. So if I were to graph this, I would divide the period into 4 parts if I wanted to graph this. So this would be 16, 12, 8, and 4. And so this would repeat itself every 16 seconds. So we do something like this. And it would end up back at 12.8 after 16 milliseconds. And in a quarter cycle, it would go to 0. Then in a half cycle, 8 milliseconds, it would go to negative 12.8.
I wouldn't be surprised if it went younger.
And then back there. All right. So just understand that function. And let's start to step